Now we've looked at how substituents can actually have regioselectivity of groups. We can think about how we can synthesize benzene derivatives with multiple types of substituents on the ring. So we're going to see that in all cases, regioselectivity is controlled by the most activating substituent. So if I have two particular substituents on the ring, um, the one that's most active or activating is going to direct that third substituent onto the ring. Let's take a look at a couple of examples. In the first one, I have paranitro-toluene. And when I think about brominating paranitro-toluene, this particular example is relatively easy. At least it should be. Why? Well, because the methyl group is an ortho-para director, and the nitro group is a meta director. So for the methyl group, that methyl group is going to direct bromine into the ortho positions or the para position. Now, obviously, the para position is taken by the nitro group, and so it's not going to undergo substitution of nitro. I see this as a common mistake. The substituents that are on the ring are going to stay on the ring in almost all cases, and in all cases of electrophilic aromatic substitution. And of course, the nitro group is going to want to direct meta to it, which is ortho to the methyl group. And so you see that it's going to direct in one of these two positions. And of course, when I brominate the ring, I get this as my product in 100% yield. So that's an easy case. Let's look at a little bit more challenging case. In this particular example, I have an amine, a methylamine, and a chlorine. Now we know that amines are OP directors. We also know that halogens are also OP directors. So now we have a clash between regioselectivity, right? The amine is going to want to place the bromine onto ortho to it, and the chlorine is going to want to place bromine ortho to it. Which one wins? Well, notice I said regioselectivity controlled by the most activating substituent. We know that amines are highly activating. We know that halogens are actually mildly deactivating. So the amine is going to control the regioselectivity, and we get bromination ortho to the amine, meta to the chlorine. So it's going opposite what chlorine would expect, but that's okay because we know that the amine is more activating toward that position. So are there other factors? Definitely there are factors to consider when you're adding substituents onto the ring. The first big factor is thinking about the order of introduction of substituents so that we ensure the correct orientation onto the ring. The second factor to consider at times is that Friedel-Crafts reactions can't be carried out on strongly deactivated rings. Now notice I say strongly deactivated rings. If I have a halogen on the ring, that's a mild deactivator, and of course we can get Friedel-Crafts reactions to occur. But anything stronger than halogens and Friedel-Crafts alkylation or acylation reactions cannot happen. There's no reaction that occurs, and so we have to think about that when introducing substituents onto the ring. And third, sometimes CR reactions have to be combined with functional group transformations. You might have a substituent that is a meta director, and so you might have to start out with something that's ortho, an OP director, and then transform it into a meta director. And so those types of problems can crop up. The fourth issue has to do with reactivity. When you have a highly activating group on the ring, you can often get more than one substituent to be placed on the ring, basically. So here I have meta-amino benzoic acid. And if I treat this with an excess amount of bromine, of course the NH2 group is more activating, and so the bromines are directed relative to it, and they go ortho to it and para to it. And notice I get a tribromination, right? And the reason for this is simple. Right? We get a very good yield because that NH2 group is a strong activator. Now, one question might be, well, what if I want to add one bromine onto the ring? So if I start with aniline and I simply want to undergo monobromination and get parabromoaniline, how do I go about doing that? Well, it becomes very difficult to do so. Why? Because as we just saw, aniline strongly activates the ring, and so you get a mixture of mono, di, and tri-substituted products, even if you try to control the stoichiometry of bromine. So you get multiple substitutions, you get a mess happening. It's the yields are very low of simple parabromoaniline. The way that you can work around this is by, in essence, deactivating the NH2 group. As we saw on our table, amides, so N-C double bond O-R, are much less activating than amines are. I can create an amide from an amine by simply reacting the amine with an acyl chloride. Right? So here I have aniline. I'm reacting it with acetyl chloride, and I get this as my product. This is called acetanilide. Acetanilide. It is an amide. And the nitrogen is less reactive than the nitrogen on an amine. And the reason for this has to do with that carbonyl. The carbonyl is withdrawing electron density from the nitrogen. And as a matter of fact, we can draw a resonance structure where the nitrogen donates a pair of electrons to the carbon. The electrons from that carbon-oxygen pi bond go up to the oxygen, right? And so we see that the electrons from the nitrogen are being withdrawn slightly from the ring. So there's a competing, there are two competing groups that are vying for those electrons, the ring itself and the carbonyl group. And so this actually comes in handy because if I brominate acetanilide, I can brominate it with excess amount of bromine if I want to, and I only get monobromination. So here I get parabromoacetanilide in very good yields. Now obviously this is not parabromoaniline. How do I get back to parabromoaniline? Well, it's relatively easy because acetanilide can be hydrolyzed. And if I take and I react it with aqueous basic conditions, here's sodium hydroxide in water, I can now hydrolyze the amide and free up my amine, and I get parabromoaniline in very good yields. Here's another example where we have a highly activating substituent, OH group, right? We know that that's on the top of our table. And of course, if I add excess bromine to phenol, I can get tribromination in very good yields. Now, phenol is a little bit easier to control, and if I want to brominate it, monobrominate phenol, I can actually do so. And the bromine always goes to the para position. So the yield of this is 100%, 100% parabromophenol. Now, the question is, well, what if I don't want parabromophenol and instead I want orthobromophenol, right? We know that phenol is an OP director. What if I want to emphasize the O in the OP? One way of doing this is by taking phenol and reacting it with sulfuric acid. So we're talking, again, we saw that with benzene you need fuming sulfuric acid to sulfonate. With phenol you simply need normal concentrated sulfuric acid. And when I do that, of course, the electrophile isn't quite as good, and so I can actually control the amount of uh, of uh, of HSO3s that I put onto the ring to 2, right? I'm adding an excess amount. Only 2 of those 2 SO3Hs go onto the ring. And so now notice I still have a spot there ortho to the OH group. I can add bromine to it, and the bromine is going to be directed by the OH because OH is a strong activating group. The sulfonic acids are weak, they are deactivating groups, so OH controls the regioselectivity. And so now I have to get those SO3H groups off. Well, if you remember, in sulfonation, when I introduced that topic, I said that those reactions are actually reversible, that I can remove that sulfonic acid group simply by adding water and heat. So in this example, I can add water and heat, I remove the sulfonic acid groups, and I end up with orthobromophenol. All right, so let's see how that order of introduction kind of plays out. What if I wanted to make parabromoacetophenone, right? Acetophenone is a ketone with a methyl group and a benzene ring attached to it, right? So this is called parabromoacetophenone. And I want to make that from benzene, originally from benzene. How would I go about doing that? Well, you see that the order of introduction of substituents becomes very important. If I take benzene and I treat it with acetyl chloride and aluminum chloride, so I'm undergoing a Friedel-Crafts acylation, and I'm going to put that acyl group onto the ring. So now I get acetophenone. Now, acetophenone, in terms of its regioselectivity, is a meta-director. I want para-bromoacetophenone. If I take acetophenone and I try to brominate it, I'm going to get meta-bromoacetophenone. And obviously this is not the correct product. So I have to backtrack. And I see that if I react benzene now with bromine, I brominate first, I get bromobenzene. Bromobenzene, the bromine, is an OP director. And this is exactly what I want. So now I'm ensuring correct orientation of the substituents. I can acylate it, right? So I do a Friedel-Crafts acylation. Always, when you do a Friedel-Crafts acylation, you want to determine is the ring active towards substitution. Bromine mildly deactivates, but not strongly deactivates, so we can get a Friedel-Crafts reaction to occur, and we get our correct product. And here's another example where we have now meta-nitroacetophenone. I want to make this again from benzene. How do I go about doing that? Well, this looks easy at first because, as we saw in our previous example, acetophenone is a meta-director and the nitro group is a meta-director. And so it shouldn't really matter how, which one I introduce first because they're both meta-directors. Well, let's take a look at what happens. If I nitrate first and I get nitrobenzene, notice nitrobenzene, the nitro group is a meta-director, and I should be able to then put a substituent meta to it. But it also strongly deactivates the ring. And we saw that when you do a Friedel-Crafts reaction on a deactivated ring, there are no reactions that take place. So no Friedel-Crafts reactions can occur when you have a deactivated ring. So always remember that. Instead, we can acylate it first, right? And we get acetophenone, and now we can easily nitrate it, just like we saw in the previous example, right? Bromine, with bromine, it would go in the meta position. Here, the nitration also going to go in the meta position. This time, that's exactly what we want. We want meta-nitroacetophenone. And so this is what we're going to be working on throughout this chapter is thinking about how we introduce substituents onto the ring.